So far, we've been looking at two-dimensional pictures, if you want to think about the graph of, say, f of x with respect to x. And we've used Riemann sums to approximate area under the curve. And the way we do that is we take the desired two-dimensional region and we chop it up into rectangles. And you can start to think about that same idea that if I want to approximate volume, perhaps I can take my three-dimensional shape and chop that up into smaller pieces and aggregate the estimate of each of those small pieces, their volume, to get a total approximation. So we call this slicing, which is, like I said, exactly what we do when we're looking at Riemann sums to approximate area. But here, instead of having a rectangle, my slice will be something that will also be three-dimensional, and we can find the volume of a slice. So rather than kind of go through a broad overview of this, I think it's actually more advantageous to look at specific examples. In this video, I'm going to look at particularly at using slicing to look at the volume of a cylinder, but we'll also look at other three-dimensional shapes so that the technique is clear. You'll see what's similar in the process, but also as the shape changes, we can see how does that affect certain steps along the way. So in this example, I have a cylinder that I've sketched here. Their base radius is 2 and the height is 10. And we want to find the volume of this. Now, you very well might know a formula for finding the volume of a cylinder. I don't want to use that in particular here. And as the method we put together here, we'll start to be able to find the volume of shapes that maybe you don't already have a formula in mind for. And in particular, what's interesting about this is we're going to end up with what we would expect to find for the volume of the cylinder, but we'll be able to get there via an integral. So to get to that integral, I actually want to start by focusing on the slices and thinking about an appropriate Riemann sum. So looking at this cylinder here, I will say there are choices about how I slice. I'm going to slice it horizontally. So thinking about this, if you were to cut this horizontally, just a very narrow cut, there would be some kind of thickness involved. So you can imagine this here. And just for reference, we're going to shade this in as green. This is going to be my representative slice that I'm looking at here. Now, notice that if I had chosen to chop this up vertically, which is completely acceptable, you would no longer have these circular type slices, but instead they would be rectangular with a little bit of a thickness as well. So in this instance, having chosen to cut it this way, what we can look at is, imagine that I'm looking at the height here, which we know the total height is 10, and I'm chopping this into n equal height pieces. So I'm going to take the total height 10 and divide by n. This is exactly the same way we think about delta x when we're doing our Riemann sums. Then once I think about that, I want to be able to indicate the edge values on the height at each of those slices. And we can take the base, which we can think of as height 0. Imagine this is sitting on the ground. And then add k times delta h to get to our hk value. This is the same type of formula we used, again, when we saw Riemann sums before. And in this instance, this simplifies to 10k over n. So if I want to think about this green piece here, imagine that, I could have made it a little bit bigger for our picture. That's hk, that's hk minus 1, and I'm going to call the green region there, I'm going to call the volume of that V sub k. And you can imagine we could find V1, V2, all the way through Vn. And if we add those volumes together, then we should get the entire volume. So if I'm looking at Vk, what I want to do here is write down a formula for the volume of just that one piece. This is similar to when we look at Riemann sums with area, how we find the area of a rectangle. Here I'm looking at the volume of my slice. Now it just so happens for this particular shape, every slice is going to be a cylinder, right? You can think about it that it's a very squat cylinder. The radius is fixed. It's going to be 2. The height of this is going to be delta H. So if I'm going to find the volume of that green cylinder, I'm going to get the base area, so pi times 2 squared, that's the area of that circle, times the height, which is delta H. So if I want to find now an approximation of the volume, then using a Riemann sum, I'm going to take the sum of the approximation of volume for each slice, which we see can be expressed as 4 pi delta H. So that's taking what we saw before. So we know that that's the approximate volume. To find the volume exactly, think about what we've seen so far. I have a Riemann sum. If I send the number of slices to infinity, then we get the exact volume. So we would send n to infinity in this instance. And now I want to think about my definition of the definite integral. As I send n to infinity, we get an integral. The delta h, remember, it becomes dh in the integral form. And it turns out that the function is constant here. It's just 4 pi. To find the bounds, we have to be a little bit careful. A common mistake I see is people wanting to put the bounds from the sigma notation, but I shouldn't have 1 to n. N only has meaning in the Riemann sum because it's dictating the number of slices. When I get to my definite integral, remember that the bounds should give me information about the integration variable and what values that should range over. Here, the integration variable is height, h, and for my region, we were talking about assuming that the, because I put a 0 in here, we were assuming that the base value is 0. So the smallest possible value of h is 0, and then to get to the top of the cylinder, we would stop at height 10. So this is the integral that would give me the exact volume. If I were to compute this, the antiderivative would be 4 pi h, h ranging from 0 to 10. Plugging in these bounds, we would get 40 pi for our answer. Now, the volume of a cylinder, which we actually had to use earlier, of course, is the height times the base area. And you'll note that you do get 40 pi. So that matches with our intuition. But like I said, this technique is more broadly useful to us in instances where we don't necessarily know what that formula would be. And also, we can kind of see the idea about now we used rectangles as kind of nice objects when we were looking at 2 dimensions. And what we're going to see here is we're going to start to try to find nice 3-dimensional shapes that we can take advantage of to help us find the volume of lots of different types of 3-dimensional shapes. So there is one kind of simplifying factor in here that maybe makes this look like overkill for what we've done. And that's the idea that as the height varies, the slice does not change, right? Every single slice was exactly the same shape. They all were cylinders of height delta h and base radius 2. You'll see as we start to look at different original shapes that that's not always the case, that the slices can change as you move the integration variable around. That's just like we've seen when you integrate a non-constant function. And like what you can see here is we did end up that our integrand was a constant function. So that's something a little bit particular to this. There's something simple about this nice cylinder shape that I do end up with that constant function. So just a kind of a warning, we'll see that there's a little bit more work required when I don't have that situation. And so what we want to consider here is this process we've outlined is kind of what I'm going to follow in the other examples. Figure out which way you want to slice it. Find your delta, the integration variable. Find, say, h sub k. be able to approximate the volume for a slice, and then we're going to use that to get to our integration formula. Notice that it's not simple to see, given this shape, that we should end up with the integral of 4 pi. So the process of finding the Riemann sum was actually really important here because it actually allowed us to figure out what the integrand would have to be.